So our next speaker is Yifan Wang, who is going to tell us about from topological to non-topological conformal defects. Yifan.
All right, I want to start by thanking the organizers for organizing this very interesting conference and for giving me the opportunity to speak. So my talk will be based on these two papers that we put out with my students, Sasha, and two postdocs, Himanshu and Feder at NYU, that we put out in April and in June, and some works in progress. And as you've heard a lot in this conference, topological defects are very important. And today, we'll take a slight journey into this world of a larger class of defects known as conformal defects. So the plan of the talk is the following. We'll start by, I'll not assume that you're familiar with the subject of this more general world of defects. So we'll start with some quick motivation and also background on this more general family of defects. And I will also introduce this notion that you're very familiar in the case of topological defects, a very important notion, defect fusion, that also applies in the case of non-topological defects. And you will see that there are features that are similar to the case of topological defects, but important differences. And then to illustrate this very general structure, the fusion of non-topological defects, I'll provide a very concrete example, a very simple example, where the defect is defined by an RG flow on the localized line. And this leads to the pinning field line defect. And we'll use our knowledge about how this pinning field interact with the generalized symmetry in the system to predict the fixed point of this defect RG flow, and we'll be able to say other interesting things about the properties of this defect, as you will see. All right, so let's start from some general motivations. First of all, defects really play an important role in various areas of theoretical physics. And importantly, they also have very simple and useful description in quantum field theory, which you can use to describe or make predictions about the influence of defects on phases and properties of the underlying quantum system. So just to give you some list of examples, the prototypical example of a defect are magnetic impurities in metal. This leads to the so-called Kondo effect, which have been studied by many people. And they are described in the continuum by defect lines in the SU2-Westermino-Witten model, as explained in this seminal paper. And if you're interested in gauge theories, defects in gauge theories, then you have them constructed out of world lines of heavily charged probe particles. And they are described in the continuum by Wilson and more generally Wilson-Topf loops. And if you're a lattice person, defects and impurities also come about quite often when you consider spin chains with either impurities or maybe more familiar to you with boundaries. And then in the continuum, they are described often by conformal boundary conditions if the system is gapless. And furthermore, in the context of string theory, if you're working from the world sheet, deep rings, which are very important for various reasons, are described by boundary states for the corresponding world sheet string theory, and they're also known as 2D Cartier states. And this is probably not necessary for the audience, but special class of defects with this very important property, isotopy invariance, emphasized by many speakers, gave rise to the topological defects, and that leads to this very powerful generalization of the principle of symmetries, namely the generalized symmetries. And what's the role of the other defects from this perspective? Well, they supply the charge objects that makes these symmetries interesting. And these are the main objects that we'll be studying in the rest of the talk. As you can imagine, defects, the entire world of defects is very rich and is very complicated. To make progress, we start with a specific class of defects, which is still very general than topological defects, and they are known as conformal defects, and they are quite ubiquitous in gapless systems. And you can think about these conformal defects in various ways. One way I want to think about them is they describe universality classes in gapless systems of defect RG flows, namely RG flows, for example, RG flows triggered by local operators that are localized on the submanifold of the space-time. And they describe critical phases in the phase transitions, critical point in phase transitions in the presence of boundaries and defects in the gapless system. And they have this residual conformal symmetry that's inherited from the bulk, which is slightly smaller. If there is a p-dimensional defect, it contains this p-dimensional conformal symmetry together with some transverse rotation symmetry. And so d, 2 is the full conformal symmetry for the gapless system in the bulk. Despite having this symmetry, the defect has a very different property in that there's no local p-dimensional stress tensor or current generically. the symmetry is completely inherited from the bulk. This sets defects apart from local quantum field theory in the same space dimension. And the one important, interesting feature associated with conformal defects, as opposed to the case of topological defects, is that there are new data associated with the defects coming from a large set of numbers known as critical exponents and OP data that come from operators which live intrinsically on the defect itself. In other words, not all the operators on the defect can be thought of as just bringing a bulk operator and stuck it on the defect or volume. And this kind of data, this critical exponents, together with, for example, the overlap of a local operator with the defect insertion, they are constrained by bootstrap equations that you may have heard from conformal bootstrap talks that generalize the usual 4-point crossing equation. And the simplest type of that is this defect booster equation that involves 2-point function of a local operators in the presence of a defect. And depending on which fusion channel you take, namely fusion channel in the bulk or fusion channel with the defect, they give rise to 2 different expression of same quantity, and that leads to various constraints on these quantities together with the bulk OP data, and has been exploring these papers to study constraints or potentially classifying defects this way. But this is a very hard problem. This is a very hard equation to solve based on the technology we have, partly because this equation does not have manifest positivity. So the success that the bootstrappers had with, for example, local correlation functions, local operator data in the IC model does not directly apply in this context. So we need some actual tool. And as we'll see, that actual tool will come from considering not a single defect, as what happens in this kind of bootstrap equation, but with multiple defects. And that leads naturally to this, again, this important operation of defect fusion that I emphasized before is something very important that you're familiar with in the context of topological defects. And I want to think about this defect fusion in the following way, as a generalization of the operator product expansion in the case of extended operators. And physically, what it means, this defect fusion, is this basic binary operation in which you have 2 defects parallel to one another, and you ask, when you are far away from this set of defects in the transverse direction, can you reproduce the influence of these defects on the system by a single defect, or potentially by a single defect dressed with certain degrees of freedom? This question, of course, is well understood in the case of topological defects, and you have heard that a lot, and also in the case of topological interfaces, namely defects that interpolates between different theories, okay, related by topological manipulation, but also understood in the context of supersymmetric theories for mutually BPS defects. And as already said, this fusion product encodes important information about generalized symmetries and also the anomalies of these symmetries, as well as generalized gauging that you can implement using these symmetries. Now, in the non-topological world, the fusion has various apparent challenges you have to overcome. The first challenge is that this fusion product now depends on R because these defects are not topological. In particular, there's appearance of divergence factor in this fusion product, which are absent in the case of topological fusion. And these divergence are characterized by exponent that's inversely proportional to the transverse separation. The coefficient is the analog of Casimir energy that you're familiar already in 1+1 dimensional context. And furthermore, the fusion typically gives rise to defect that can be dressed by local operator integrated along the defect. And this can trigger non-trivial defect RG flows, so it has to be handled with care. And as we'll also see, this fusion product associated with non-topological defect will have very different properties in general compared to the topological case. So the mathematics is much less understood. So what are some things we can learn from fusion, apart from this, what I just described? So one thing is, as I mentioned before, it actually leads to a more powerful bootstrap type equation to understand the defects themselves. And this is a generalization of the familiar Carty condition that arises when you consider a 2-dimensional CFT on the cylinder with boundary condition on the 2 sides. And the Carty condition is also known as a closed open duality because it amounts to viewing the cylinder, viewing this direction of the cylinder as time direction versus this direction as a time direction. And the equality between these 2 quantities leads to strong constraints on what kind of 1-point functions this boundary state can support for the local operators in the CFT. And open question is to understand what's the generalization of this equation in a higher dimension. That's not something that we accomplish in this recent paper. I also encourage you to look at the paper that appeared shortly after. What we accomplished is a limit of this equation where this R transverse separation becomes small. In which case, we don't quite have the right-hand side, unlike what happens in the two-dimensional case. But instead, we have an effective field theory of what happened on the right-hand side. So this closed-open duality really replaced by a closed effective field theory duality. But the effective field theory description on the right-hand side, obtained by integrating modes of the mass scale 1 over R, is powerful enough to already give rise to universal predictions for this the behavior of this defect when you take one-point function in the presence of it. Okay? So the goal of the rest of the topic actually not to talk about this, but rather the interplay with general symmetries, which is the theme of this conference. So we can ask whether there are constraints from general symmetries on this non-topological defects and also their fusion. So first of all, whenever you have a conformal defect, you can generate additional conformal defect, and this is a very useful tool to come up with the conformal defects by fusion with topological defects. And this process is topological. Fusion of conformal defect with conformal non-topological defects, topological defect is topological. And the symmetry properties of this conformal defects in the theory with a category symmetry C, they are captured by what's known as the bimodule categories over C. And this category tells you information about what happens when you fuse the topological defect from the left and the right in this 1+1 dimensional picture. It also tells you about information about how the topological defect may end on this conformal defect. And the defect fusion will naturally respect, so there's a natural tensor product structure. It's known as a relative or balanced tensor product on these bimodule categories. Defect fusion is constrained by the fact that it has to respect the tensor structure of the corresponding bimodule categories. Now, if you want to derive even stronger constraints on topological defect, non-topological conformal defects in the presence of general symmetries, one can consider a very special family of conformal defects. That are symmetric, that I denote as C-symmetric conformal defects, and such conformal defects are defined by the criterion that they commute with the topological defects in the category C. Okay? So this is the picture that you should have in mind that defines a topological defect D that commutes with category C, where Li are general topological defects in this category. And as we'll explain in the later in the talk, that there are various constraints. This kind of conformal defects are severely constrained, and we can often pinpoint the endpoint of our G flow using the symmetry information. And I should say that there are previous works on the constraint from RG flows of this type in 1+1 dimension, but for boundary conditions. And it was pioneered by this paper where I think Jared is in the audience.
Can I ask a question?
Yeah.
So, because about the symmetric defects.
Yeah.
So there is a stronger condition that you can ask that's Li times D equal D, no?
Yeah, so that would be a stronger condition. I'm not requiring that condition.
Okay, but you know if there is a stronger,
Yeah, there will be a stronger condition, but that's a much stronger condition, for example, that would require this topological defect to have integral quantum dimension.
Okay.
Yeah. Okay. All right. So this is so far is kind of abstract. So what do we know about the defect fusion already? In the simplest context, namely in two-dimensional CFT, this has been studied by various papers. So here, let me just give you a brief summary. So first of all, there are large families of conformal defects, line defects in two-dimensional CFT that have been identified using the powerful folding trick, in which case you consider instead the boundary condition for the double theory. But there's no full classification, partly because of the impossible infinite representation theory associated with Virasoro for standard charges bigger than 1. And this classification has only been done for Ising in this paper. And for this class of conformal lines, the divergence structure is relatively simple. It's determined by the Casimir energy, which you can read off from the ground state energy the energy of the ground state on the strip, okay, when you imagine you have these two interfaces. And then there's a simple definition of fusion product given in these papers by removing this exponential factor and keeping track of the leading term in this fusion product. Okay? And this is the definition of the fusion product that will generalize to higher dimensions. But even with this very explicit definition, this calculation of what the fusion product is, and give rise to another conformal defect, is very hard. But we can make some progress by using the fact that many conformal line defects are actually obtained by topological defects with relevant deformations that trigger defect RG flows. And the goal of the rest of the talk is to deduce such non-topological defect fusion using this relation to topological defects by relevant deformations. I should also mention these papers, which study even non-conformal integrable defects by relevant deformations from topological defects. All right, so before going into very concrete examples, let me just have one slide if you're interested in what the story looks like in higher dimension, and you can read the detail in this paper. So one can ponder what is the analog of this fusion product that one can define naturally as a generalization of this fusion product in 2 dimension, but now for defects in higher dimension, say of the same dimension P in a d-dimensional CFT. Okay, so D1, D2 are again p-dimensional defect in the same d-dimensional CFT, and there's a natural way to define their fusion product in a way analogous to the way that defined in 2 dimension by removing various exponential divergences that shows up in the naive fusion product. Okay, so that the right-hand side defines a finite product, namely you can measure correlation functions in the presence of this defect, and you get finite functions. And because the space-time dimension of this defect is larger and there's richer set of divergences, and that leads to generalized Casimir coefficients, and they contain interesting information about interaction between the defects, but I don't have time to talk about them in this for the time limit. But just to emphasize that you will find the general property, namely this fusion product defined as so, in general give rise to a direct sum of conformal defects in the same theory, but potentially dressed with degrees freedom localized on the defect, in general described by a p-dimensional QFT, and sometimes it's a TQFT. And this defect product has the property that is commutative. It's a codimension of the defect is bigger than 1 because you can use the transverse rotation symmetry to show that this fusion product is commutative. But it's very different from the case of topological defects in other gapless theories. Is that the non-topological conformal defects are generally not dualizable. Namely, when you take the fusion product of the defect and its orientation reversal, the trivial defect does not necessarily appear in this product. And also, because of this limiting procedure, which enables us to define a finite defect on the right-hand side, we lose associativity associated with this product structure. And we'll see that in very concrete example. Yeah.
Since you need to remove these divergences to define this product, are the fusion coefficients ambiguous in some way?
Very good question. So the point is that there's a locality. These divergences are constrained by locality. So you cannot remove arbitrary terms. And you see these terms, I didn't have time to describe in detail. They're constrained by locality and general covariance to be very specific terms that depend on curvature invariance of the defect embedded in the ambient space.
Okay, thanks.
Sorry, I was just wondering, can you get also log divergences? Because
in general you can.
Those you cannot remove.
That's right. Yeah, that leads to subtleties, yes. Good. All right. So let's now illustrate this very general discussion, make this general discussion more concrete using pinning field defect. And these pinning field defects are very simple defects. These are actually impurities first introduced by condensed matter theorists in lattice systems, and they are introduced for a very practical reason. It leads to some very efficient way to diagnose bulk phases, as opposed to measuring 2-point function of outer parameters. You can measure just 1-point function of outer parameter in the presence of this pinning field impurity. And they're defined, for example, in the context of Ising model by this particular coupling that you turn on at a fixed location in the spatial slice. And in the context of you want to study fusion, you can consider 2 such perturbations to your action by inserting this pinning field at 2 separate locations, separated by distance r. And the physical question you want to ask, if suppose this is your spatial lattice system and you have this spinning field turned on here and here, the physical question you want to ask is that if you zoom out, what is the combined effect of this spinning field impurities? Okay? And also, as I'll explain, and also in more general context, what you will find is that when you zoom out, if the impurities are of both the plus type, so as I'll explain, there are two types of long-distance behavior of single impurity. It could be plus or minus. It corresponds to the sign of this perturbing parameter H1 or magnetic field. If they're aligned, when you zoom out, naturally, well, intuitively, you will find the same impurity showing up, governing the long-distance behavior away from the impurity. Okay? You will see some parallel decay for local order when you measure it in the presence of this impurity. So we can be a little more general and define pinning field defects in the following way. So you start from any CFT and you have local operators phi. As long as the phi has dimensions smaller than 1, you can integrate it along the line, which trigger RG flow on that line, and that will flow to a non-trivial conformal defect in the infrared. Why so? This is because there's a very powerful G theorem that says that the G function has to decrease monotonically under defect RG flow, and the G function is defined as the Patin function with this line defect, a conformal line defect along the circle, divided by the Patin function of the theory without the defect. And that's the natural analog. It's a direct generalization of the quantum dimension you're familiar with in the context of topological defect. And because this defect RG flow is the flow from the trivial defect that has G equal to 1, okay, the quantum dimension identity operator, the defect RG flow necessarily creates a defect with G smaller than 1, and that cannot be trivial. Trivial means identity. Okay? This already tells you that this pinning field defect has to be conformal at large distance. And from the discussion, from the intuitive picture I just drawn, naively we would expect pinning field to have very simple fusion rule, namely it fuses to itself. This is also the reason that these defects are conformal defects. This is an example of a conformal defect which is not dualizable. Okay? And as we'll see, this feature together with other fusion product allow us to also see the feature of non-associativity associated with this fusion of non-topological conformal defect. And for the rest of the talk, we'll be describing how we can use general symmetries to identify the IR fixed points that describe this pinning field defect. And we'll also encounter the interesting observation that the pinning field defect that preserve symmetry are special in the sense they are stable. They do not admit any relevant deformations that preserve the symmetry. Okay? So, and they lead to something known as the self-organized critical impurity. And if you know about self-organized critical phenomena, you know they're extremely rare, but they seem to be quite common when you consider these impurities. All right, so here is an example that to attack this problem, we'll use two approaches, one perturbative and one non-perturbative. Because of the time, I'll be brief on this. It's perturbative because you can study the pinning field defect in 3 dimensions using 4 minus epsilon expansion. And this is perturbative because this pinning field phi has dimension is very close and smaller than 1 in 4 minus epsilon dimension. And that enables you to study this RG flow using perturbation theory. And you will have perturbative fixed point and allow you to pinpoint what this conformal defect, what is a conformal fixed point for this pinning field defect. And using that information, you can figure out the fusion product, and you find that fusion product takes the following form. So I should say that the pinning field defect in this case are labeled by a vector on the n-1 dimensional sphere and tells you which direction in ON where the pinning field points. And the fusion product is very simple. It's very intuitive. It's namely that the average between these directions associated with the original pinning field defect that you fuse. In the particular case of ink to 1, namely the Ising case, you find this fusion product that we already saw before on the lattice slide. And similarly, you'll find that if you fuse pinning field with the magnetic field aligned the opposite direction, you get the expected answer. But when you fuse this anti-aligned pinning field, you get the trivial defect. Okay? And combine this together is a small exercise, and you can see that it's indeed not associative. Okay? Just try plus, plus, minus. And in the more general case, like in the case where you do not have access to perturbative fixed point, which happens in various flows, pinning field flows into the dimensional CFTs, we can use symmetries. So I should first say that in two-dimensional CFT, there are large families of pinning field defect that you can get by turning on operators of dimensions smaller than 1 along a line. And for example, all defects in the icing can be obtained this way if you slightly loosen this condition by allowing the dimension of the operator to turn out to be dimension 1. So they lead to marginal deformations on this line defect. And a very interesting feature and common feature associated with pinning field defect in 2 dimensions is that it actually leads to factorized interfaces in 2-dimensional CFT. And this greatly enhances our ability to determine the error fixed point. And the way we see that is to start from this picture, that this defines the pinning field defect. And this picture can be traded with a different picture, where instead of turning on this deformation on the line, you can turn on this deformation on the strip. So this trades this RG flow on the line defects by RG flow in the bulk restricted to a strip. And as far as you are zooming out and looking at long distance, this defines the same line defect in the infrared, as long as the OPE of phi itself does not produce more relevant operators. Okay? If you like the Hamiltonian language, you can imagine that this amounts to a modification of your Hamiltonian by integration of this phi on the interval. And if you're looking at the very large spin chain, then the effect is equivalent given by this perturbation. Now, this picture, if this phi operator deformation gaps the theory in the bulk, under the bulk RG flow, that gave rise to the TQFT, which are denoted by T gap. And in the TQFT, you can insert a complete set of states that factorize the theory using the Carty brains. And once you have done so, you can fuse the TQFT region, remove the TQFT region by fusing the red topological boundaries onto the interface between the physical theory and the topological part, and you get a direct sum over boundary condition of the bulk theory. And this is how you get the factorized, you get what we promised over here, you get a factorized interface that describes this pinning field at the fixed point. And the fact that this factorized immediately tells you that the pinning field fuses to self is a common, it's a feature that is followed from factorization. And then you can fix what kind of factorized defect it is by enumerating what kind of boundary conditions you have in a given CFT, which we have complete classification in the case of minimum models. And then you can restrict the possibility using the symmetries. If, for example, you have a symmetry that commutes with the pinning field, then it leads to this C-symmetric defect, which I defined before. And then, for example, the symmetry structure associated with the defect, namely the bimodule category structure, can be determined by the TQFT in the strip. And if the module category labeled the TQFT is denoted by M gap, which is a module category respect over C, left over C, but is also a bimodule category over C and C dual. You can do this tensor product, and using results from these papers, you can do a simple analysis, and you find indeed the tensor product of this module category M, bimodule category M, does reproduce M, as you expect for the pinning field defect to be consistent with this fusion. All right, so just to give you wrap up with 2 examples. So in the case of icing, there's a single operator with dimensions smaller than 1, namely the sigma operator. Has dimension 1/8, and this operator fits the bill for this factorization to appear because both conditions are satisfied. First of all, the condition that sigma gaps the theory is satisfied. The theory is known to flow to a trivial state with a unique ground state. Then a trivial phase with a unique ground state. And also the OPE of a sigma operator does not contain more relevant operators. You just have identity and energy operator. Energy operator has dimension 1. And the boundary states of IC model is also classified. It's just plus minus correspond to dirichlet boundary condition for the spin on the boundary and the free boundary condition, okay, where you do not put any constraint. And using the discussion we just, general discussion we just gave, you can easily figure out what is the endpoint of this RG flow. It has to be a direct sum over boundary condition paired like this, like plus plus minus minus or FF. It will be a general direct sum of that. But FF is forbidden because F has G function equal to 1, and the identity line has G equal to 1. And as a consequence of G theorem, the only possibility are these 2. Okay? And you can also check that the fact that the plus plus and minus minus are related by Z2 symmetry is consistent with the fact that the sigma operator is odd under Z2 by running this picture. And then once you have identified these endpoints, you can check that indeed the fusion rule takes the form that we said before, follow from general discussion. But this didn't follow from the general discussion, and it's very subtle. But in this case, you can see explicitly that D plus D minus give rise to this new factorized interface, and its non-commutativity is transparent by doing the fusion product in the other order, whether you get minus and plus. factorized interface. Now, the more interesting example is the tricategorizing model. I'll be very brief. In this case, you have 6 primary operators, and there's an interesting symmetry to play with, namely the Ising times Fibonacci category symmetry. And there are 6 elementary boundary states in this theory. And as we said before, as long as we look at Pini field that triggers a bulk RG flow to a gap phase, it's sufficient to focus on the boundary state to cook up candidates for this factorial interface that describes the IR fixed point of this Pini field defects. And this boundary state is also related by fusion with this topological defects in the following way. In particular, the plus and minus related by fusion with the Z2 generator, plus and 0 related by fusing with the N generator, and this plus and 0 minus are related by fusing with the Fibonacci generator. And this plus minus 0 are a notation that come from a particular lattice model realization of tricategorizing model, where at each side you have 3 degrees freedom labeled by spin plus, minus, and 0. And this notation are similar to the case of Ising in defining boundary condition on lattice. And among this list of operators, 6 operators, there are 3 operators which are non-trivial and have dimensions smaller than 1. And they preserve the following symmetries. This operator preserves Z2. The sigma operator preserves no symmetry. The sigma prime operator, interestingly, preserves the Fibonacci symmetry. And it's well known what is the fate when you turn this deformation in the bulk. In particular, over here, you have symmetry breaking of Z2, and you have a trivial phase for the other sign. And then for sigma, for this operator, preserve no symmetry. As you would expect, the phase is completely trivial for either sign. And for sigma prime operator, because of these two phases are related by the Z2 symmetry, you get the isomorphic phases, namely symmetry breaking with 2 degenerate ground states. Now, to combine with the factorization, which is general result based on the conditions which are satisfied in this particular example, and G theorem, and together with the symmetries that are preserved by this pinning field, you can completely pin down what are the possible fixed points for this RG flows due to pinning field. And these are the answers. Okay? And I welcome you to check that in all the examples and also in other examples that you can come up with, this even though it looks like they may be unstable, because typically we have a direct sum of defects. When the defect is not simple, you may expect there to be relevant deformations that prefer one or the other. They are forbidden because of the symmetries. Okay? So all these interfaces that come from the pinning field deformation are stable. They are self-organized critical impurities. Okay, so let me end by discussing listing a number of future directions. The first future direction will be generalizing this kind of strip RG flow picture to come up with more class of conformal defects. And for example, you can consider instead of RG flow in the strip that complete gets the theory, consider RG flow that leaves the gapless phase in the infrared. In which case, you can still talk about the conformal defect that come from the fusion of these 2 interfaces, okay, the RG interfaces which was introduced in this paper. And also kind of motivated by this observation that the pinning field are stable fixed points preserved by symmetries, RG fixed points by symmetries, one can contemplate maybe there's a lower bound on the G functions of defects that commutes with certain generalized symmetries by the G function of the pinning fields. And this may lead to some symmetry enriched G theorem, which is analogous to the symmetry enriched C theorem for certain rational conformal field theory discussed in this paper. And furthermore, I didn't have time to discuss, but this there are interesting games you can play to generate new conformal defects using gauging, generalized gauging, and also as well as generalized higher gauging. And furthermore, there's an interesting paper by Christian that appeared shortly before the conference that can be used to study this kind of symmetry constraints for defect RG flows in higher dimensions. With that, let me thank you for.
We have time for a few questions.
Hi. So, suppose you have a defect which flows to a topological defect in the IR.
Yes.
Is there some relation between the fusion of the conformal defect and the symmetry that you get in the IR?
Very good. So let's see. The short answer is I don't know. What I know is that if you start from the topological defects in the UV And then you can learn about the fusion product of the conformal defect that you get from the deformation. And in the special cases where the relevant deformation of the topological defect leads to another topological defect in the infrared, you can extract that information. But in the more general case where you have a flow from a conformal defect to a topological defect, I don't know the answer. So this is related to the paper I mentioned by Runkel. The flow from topological to topological defect is related to this paper I mentioned. Sorry. This paper I mentioned over here.
I have a question. I have many questions, but I will just...
Okay.
So, in this case of 2D interfaces, you can always do folding, no? And as boundary conditions.
Yeah.
What is the analog of the deformation that you did? This is a simple analog of the relevant deformation for the boundary condition. It's just deformation by one boundary operator on one side or something.
Yeah. But it's it's slightly more general, right? So so for factorized interface, you can describe this. You can describe deformations of this interface by product operators that correspond to boundary changer operators on either sides, but they're more general operators.
Okay.
Yeah.
So you can describe also the guys which are non-diagonal in this set.
That's right, and you can take multiple such operators.
Mm-hmm.
Yeah.
Okay, that's much more rich.
That's right. So there's a very large RG phase diagram, RG diagram that you can consider by taking on multiple deformations. Yeah. So here I'm considering the simplest case.
Let's leave other questions for the break, and thanks, Yifan, again.